Hello and welcome back to the channel. And we are today at day 12 of Advent of Code. Can you believe it? We are almost at halfway of the challenge. And in this whole series, I have been really trying to embrace the spirit of Christmas and the challenge. So today I present this video to you from a dodecagon, a 12-sided polygon, the camera frame that you see around me. And fun fact, ancient Greeks used to think that dodecagon is a symbol of zodiac. Pretty cool, huh? Well, if you're new here, I am Jatin Kumar Malik. I'm a principal engineer who absolutely loves solving puzzles, and what better time than December Advent calendar to solve Advent of Code. And if you have missed my last 11 videos with the spoiler-free discussion of how to solve the problem, where I go behind the scenes for problem solving and how you approach a problem before you even write a single line of code, do check it out. A lot of effort has gone into doing this along with my full-time job, and it takes a lot of time to record this, edit this, and publish this. So some feedback would be really nice. So with that, let's quickly jump into day 12. And the day 12 problem today is called garden groups. So let's read it. So why not search for the chief historian near the gardener? We are still searching for chief historian, by the way. He got lost somewhere in day 1, and it has been 12 days, and I'm still trying to help these elves to find him. So yeah, so near the gardener, I think this is a reference to 2023, day 5, and his massive farm, and another reference to 2023, day 21. So there is plenty of food, so the historians grab something to eat while they search. You are about to settle near a complex arrangement of garden plots when some elves ask you if you can lend a hand. Absolutely. They would like to set up fences around each region of garden plots, but they cannot figure out how much fence they need to order or how much will it cost. They hand you a map, that is our puzzle input, of the garden plots. So our input here is a map of garden plots. Okay, let's read on. So each garden plot grows only single type of plant. So we will call a garden plot a GP, and each of them grows a single type of plant and is indicated by a single letter on your map. When multiple garden plots are growing the same type of plant and are touching horizontally or vertically, they form a region. Oh, so each plot can be a letter. So A to Z, it seems like for now. And what it says is that when multiple garden plots are growing in the same type of plant, they are touching, they form a region. I got it. So we are given an example of a 4x4 grid, and let's see. So this 4x4 arrangement includes garden plot growing 5 different type of plants labeled A, B, C, D, E. We can see that here, and each grouped into their own region. In order to accurately calculate the cost of fence around a single region, so we have to build a fence around a region. And in order to calculate the cost of fence around a single region, you need to know what region's area and perimeter is. That seems interesting. And the area of region is simply the number of garden plots the region contains. So that's simple. And in the above map, type A, B, and C plant each are in the region of area 4. So if we have to see this, we can see like A region is here, B is here, C is a little abstract where we are going like this. Then you have E here, and then you have D here. And if we want to see, A is 4, B is 4, C is 4, E is 3, and D is 1. And I think that's what they are saying here. So A, B, C are each in the region of area 4, and the E-type plant are in the region of area 3, and D is in the 1, exactly. And it's said that like our area is just the number of plants in a region that is given to us. Let's read on. Each garden plot is a square and so has four sides. So we can see the four sides here. So they're saying that it is always going to be square. So 1, 2, 3, 4. So we have four sides. Nothing new here. The perimeter of region is the number of sides of garden plots in the region that do not touch any other garden plot in the same region. The perimeter of a region. So if you want to calculate a perimeter of a region, it will be the number of sides of garden plots in the region that do not touch another garden plot in the same region. I see. So the type A and C are each in the region with perimeter 10. Type B and E plant are each in the region with perimeter 8. Lone D plot forms its own region with perimeter 4. I see. So basically we are calculating the perimeter of each plot. So remember, this each individual item is a plot. So what it's saying is if we are calculating for A, so it's like counting like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly for B, we are calculating 1, 2, 3, 4, 5, 6, 7, 8. Is that correct? Yep. And for C, it's basically the boundary. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For D, it is going to be 1, 2, 3, 4. And for E, it will be 1, 2, 3, 4, 5, 6, 7, 8. So we got that. And if you had to check, it seems like that's correct. So there is a visual representation including the sides of the plots in each region that contribute to the perimeter using dash and pipe. And the above region perimeters are measured as follows, which is basically the blue lines that we have drawn here. Let's read on. This is a large question. So plants of same type can appear in multiple separate regions, and the regions can even appear within another regions. Oh, so this gets complex. So for example, we are given an above map. Let's get this here so that we can evaluate that. And we'll make this a little bigger. Like this. So in this example, it says that if I had to pick red color, it contains 5 regions, one containing all of the 0 garden plots, which means like this is not just A to Z. This can also be 0 to 9. Going back. So this is good to build upon your knowledge base and write things down so that you have all requirements in one place. And this contains 5 regions. So if we have to check, we can see you have 1, 2, 3, 4, and 5. So this is like an example of a region within a region. So we have a region in region. And they all contain zeros, and the 4 each contains of a single X plot each. Exactly. So the 4X region each have area 1. So the area is nothing but the number of elements, number of plants inside a plot. So X has area of 1. So let's say X of area 1, and the perimeter is 4. And a quick reminder, perimeter is nothing but we are calculating the adjacent sides of a region. So 1, 2, 3, 4. 1, 2, 3, 4, and you get the idea. But the more interesting part is if you want to calculate the area for 0. So for area for 0 would be, this is a 5 by 5 matrix. So 5 into 5, 25 minus 4 should be 21. And yep. And the perimeter is the more interesting one. So since this is perimeter, like the more gaps something will have, the more perimeter, like more areas you will have to scan for perimeter. But let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Is that correct? Yep, that's correct. Okay, it took me a while to check. So it's doing the same thing here where when we are calculating the perimeter, it first calculated the outer bound, which is 20, and then it's additional 4 each for, so 4 into 4 each for each of the x plots in between. That brings the total to 36. So that's correct. We have an understanding of the problem. So now, due to modern business practices, the price of fence required for our region is found by multiplying that region's area by its perimeter. Okay. The total price of fencing all the regions on a map is found by adding together the price of fence for every region on the map. Got it. So let's take another color here. So now you need like cost of fencing, the original question. And the cost of fencing is that per region, we have to multiply a area by its perimeter for R1, and then you will do for R2, you will multiply by area with the perimeter and so on. So if we have to go for this example, in the first example, so let's go back up. If we had to calculate the price here, I think they have given the formula where region A has an area of 4 and it has a perimeter of 10. So the cost here, like the dollar, like cost would be 4 into 10, which is 40 units. Similarly, region B, that was here, which had an area of 4 and had a side of 8. So that would be 4 into 8, 32. And that's correct. Similarly, region C has area of 4 and the perimeter of 10. So that would be 4 into 10, 40. And coming back to area D has an area of 1 but a perimeter of 4. So the cost would be 4. There is also E. And for E, the area is 3 and the perimeter is 3 plus 3, 6 plus 2, 8, which is 24. So our sum of total cost of fencing this input would be 40 plus 32 plus 40 plus 4 plus 24, which comes around 140. And similarly, we can, and my recommendation to you is while I'm walking through the problem, it would really help you if you could do this yourself on a copy with a paper and pen. So similarly here, it said like 0 plant has a price of 21 into 36. So we already calculated 21 and 36. So if you have to calculate the cost below this, it would be 21 into 36. That's the O plus. We have X, so 1 into 4. So we have 4 into 1 into 4. So I'm just improvising on the maths. So that would be for X. And the total answer comes to 772. That is for this puzzle. So now we are given a larger example where we have multiple crops. So we have R, I, C, F, V, M, S, J, A. And then it has given us the same example where we are doing like a calculation. So I'm going to skip this in interest of time, but it's a good exercise for you to do like a dry run of this puzzle as well. Maybe use an interactive whiteboard and do that. And we are calculating the price. And now we are given a puzzle input. Let's take a look at that. And it seems pretty huge, right? So going back, now what we need to do is looking at the puzzle input, we need to get the total price of fencing all the regions on the map. Now that we have done a walkthrough of a problem, I think it's a good time for us to pause, and you should pause here and try to think about how you will solve this problem. And once you are back, we will talk about some of the strategies that are going through in my head, and then I will walk you through on how I think I'm going to approach this problem before writing a code to build a common logic, which is the most important part of solving any puzzle. So yeah, I'm not joking. Pause now, think about the problem, and then come back, and then we will discuss further. All right. I hope you paused and gave this question a thought. Yeah, I trust you. So let's talk about some of the hints and how we should approach this problem here. So if you see, One of the first things that you should always think when you look at a problem like this is like, what data structure would you use to represent this? And so represent this. And what do you want to then do with it? And if you look at this question and the examples that are given to us, it looks like I think one of the first things is like that rings bell in my head is like a graph traversal slash connected components kind of a problem, where you have to find the region, which is nothing but the connected garden plots of the same crop. And with questions like this, I think we have seen this in past few days as well. The devil is in the details, right? Like a lot of English is just the fluff around the basic problem. And once you do some of the dry runs and you break down the problem, writing the actual code is not that difficult. It becomes really trivial, right? So what I'll do is I'll take this example, and I'm not going to do a whole dry run, but I'll just walk you through like maybe one of them, and that will help us build some logic. So if you see, if the first thing we have to do to find the cost is breaking down the cost formula that we wrote here is to find a region here. And once you find a region, the next thing is that you need to find the area. Like if you are breaking down the problem into the smaller sub problem. So this is a sub problem right here. We need to find the area, we need to find the perimeter, and then by multiplying them, we get like our cost 1, C1. Similarly, we do it for region 2, get our C2, and so on, and then overall we have the answer. So coming back to this, when you look at this, think about you are the pointer, and how will you find these regions first, right? Like that is the first order of business. Like what all regions do we have here? And if we could have like maybe a group of regions, calculating area and perimeter is the second problem. So we will go back to that, but let's see. So when you are looking for a region, let's say if you start here, how would you do it manually? I think this is one of my favorite ways of thinking about programming and coding. A lot of times, everything you see in coding, especially object-oriented programming, I think they used to teach us in the school that it is modeled after real life, where we have classes and objects. And I'm not talking about that we are living in a simulation or this is a matrix, but if you think and look around everything that you have, everything can be modeled in object-oriented programming. But coming back to the problem, if I have to do it manually, like how my eyes scan, like humans are really good at finding patterns. You can quickly see that my eyes scan like this. And then as soon as it reaches I, it stops, it goes down. It tries to find all the R's it can. It does. I see what else is connected. This is connected. And this is connected. And if I draw like a neat and clean boundary around that, this is nothing but like one of our regions in the question. And similarly, like let's do the same exercise for I. So my I starts from here. My eyes goes to I. It sees that, oops, this is C. Can't go right. Let's go down. Can't go right. Can't go down. Let's go left. And we are back to the visited node. And this is our another region. And let's do the same thing again for maybe V here. So we start from V. We go left. We go down. We go right. And it's very intuitive. Like it's basically like filling colors in a notebook. And you can see very quickly how just using my pattern identification algorithm in my brain, which is like some organic encoded algorithm, like it seems like this is the theme of the episode. It's very easy for me to identify these regions and do that. And let's do one more. So maybe we'll do one here. So starting with this M, I can quickly see that this is my another region. So that's the first order of business. And if you look at this carefully, what are we doing here? We are doing nothing, but we are doing a simple BFS/DFS search, which is nothing but a graph traversal algorithm, where you pick one side and then you start looking up, left, bottom, and right. And this is something we have done in a couple of problems in last few days. I will probably link them here if you have not seen them. And once you start traversing, you keep going till you keep finding the same plant crop, which is basically the same element. And as soon as you have exhausted and visited all the nodes, you have your region boundary. And then you can store it representing this is very easy. There are multiple ways, but a simple way I can think of is like a simple x comma y comma b, like an array of a coordinates list, and then like I can maintain like multiple list kind of an arrangement. So that's our first order of business. And let's say now that you have this region, now second order of business is to find area. Area is rather simple because it will be nothing but the length of the region, and that's all. And let's talk about the third one. The third one is perimeter. So yeah, let's talk about the perimeter. And to find perimeter, you basically can just start from any plot, any plant or plot in the region. And once you do that, you start with your perimeter at 0 and you start looking at the adjacent neighbor, right? So as soon as you start with something, you add 1 to this. And now let's say we follow the same BFS approach that we were doing. So if you go right and you find that it is the same neighbor that you have visited, you will go right. And the idea is that whenever you're calculating the perimeter, you don't care about the internal detail. All you care about is finding the edges and the boundaries. And the same story is here. And you come here, and here also you look at right. Is it the same type of plant? It is. You add 1 to the perimeter, move right. You keep moving right until you hit another. Okay, add 1. And then as soon as you move to another one, you see that, oh, this is another plot. So you cannot go here. And you cannot go left because that is a visited node. You have already counted that for a perimeter and it was an edge node. You cannot go up because you are on the edge of the input puzzle, which is your map. And the only possible direction for you is to go down. So when you go down, you add 1 to the puzzle, but you have not started looking at the neighbor yet. That's the only possible place for you to go because you came from the left side, so you cannot go into the negative direction of the direction you are heading. So there is a direction vector that comes into the picture here. And then while going down, again, you follow the same thing. If you find the exact same number, you add 1 to that and you move to it. And then you again look at all the neighbors. So you look at the right side, it's still another plot. You cannot go there. You cannot go up. You definitely can go right, but since you are moving, your direction vector is down, you will first check if you can go down. And it seems like you can go down. So you will go down, you will add 1 to the perimeter. And now again, same thing. You cannot go up because that's where you came from. It's the negative of the direction you're moving in. You will first check right. So to see if you can go right. In this case, it seems like you can go right and you can also go left here. But since you have been coming down, you will check in the same order. You will go right. And after moving right, you will add 1 to the perimeter. You will look up. It's still the other one. Can't go up. You will look at the right. You can't keep going right. You cannot go back. So the only direction that is left is for you to go down. So you go down, add 1 to the perimeter, and you follow the same step. And you keep doing this till you reach back to the point where you start for with the same direction vector. That is very important because as you can see on this corner element, this contributes to two sides in perimeter. But for something like this element, it only contributes to one side. So having a direction vector to store when you're traversing the perimeter is really important. And once you do that, you will get the perimeter. And once you get the perimeter, all you need to do is you need to maintain a cost where you will again run back the same formula that we wrote here, which is the area into perimeter plus region 2, region 3, region 4, and so on. And you will do it till you exhaust all the regions. Once this is done, you get your answer and you return it back. So I hope that helped. And trust me, once you do a dry run on this example, it will help you a lot in clarifying some of these issues. And what I will do is I will now go back and write some code so that we can unlock part 2. And we will do a quick retro after I solve part 1 to discuss if there is anything else we could have done to optimize it. And we are burned from the last day's brute force approach. But it seems like here there is no other way, right? Like there is no way to solve this without looking at each and every element, because to calculate regions, you will have to look at these boundaries that are being drawn. So there is no way without looking at each and every element. So I think we should be good. There are definitely some optimizations, but we will discuss it once I'm back with the code. So good time for you. Open up that IDE terminal, NeoVim, Vim, Emacs. I don't judge, but go ahead and write some code, and I will see you in a bit then. Hey, welcome back everyone. So as you can see, we got our first gold star and we solved the problem. And the part one was quite the garden party. To solve this, I basically followed everything that we discussed here. I think one enhancement I made that instead of finding the region and then finding the area differently, I just wrote like a iterative. I initially thought I will go recursive, but then I wanted to keep my code a little simple and intuitive to understand. So I followed an iterative DFS where you will call it from a larger for loop, and you will pass each element. And whenever you pass an element, the job of this method would be to go and find the outer bound of the region and then internally find a region and then return back both perimeter and area using a helper function. And then in this larger loop, once we have perimeter and area, we can just maintain the cost and calculate the cost and return that. And in case you are stuck here, I will push my well-documented code to GitHub repository. Take a look at that. I have made it very easy to follow, and I have also kept all the test cases that we have discussed in the code. So in case you want to see the flow of the code, you can put a couple of debug points on the test cases and then just walk through it. And especially the initial one that was fairly small, this one here. So with that, we have unlocked the part two. Let's go ahead and see what more complications lie in our way. And I'm especially scared after yesterday. Okay, so fortunately, the elves are trying to order so much fence that they qualify for a bulk discount. Interesting. So we have something called a new construct for bulk discount. Under the bulk discount, instead of using the perimeter to calculate the price, you need to use the number of sides each region has. Each straight section of fence counts as a side, regardless of how long it is. So I think one interesting thing here is that now we are not interested in perimeter. So perimeter was sum of all the sides of individual garden plots, but we want to use the simple number of sides of. An easy way to understand is that the shape of region. So if it is a, like what side polygon it is, like if you look at my camera, this is today our day 12. So it's a 12-sided polygon where the perimeter and the number of sides are same, but that's not always the case. Anyways, let's read. So we have given an example here. So considering this example again, let me get this back to our whiteboard. If we were to draw the regions again, like we did before, we can see we have one region here, one region here, one region for C here, one for E here, and then one for D here. And now if we had to calculate the same thing, so for A, we can calculate the area to be 4, and then the perimeter, instead of 10 in the part 1, here the perimeter will also be 4, because remember perimeter is the number of sides. So we have 1, 2, 3, and 4 sides, and we don't care how long they are. Similarly for B, the area is 4 and the perimeter is again 4 because 4 sides. For C, it becomes interesting because for C, the area is 4, but perimeter in this case is 1, 2, 3, 4, 5, 6, 7, and 8. Is that correct? Yeah, C has 8 sides. And for D, area is 1, perimeter is 4. And then for E, the last one, the area is 3 and the perimeter is still 4. Yeah, and the method of calculating cost is probably still the same. So let's read that. Using the new method of calculating per region price by multiplying the region's area by its number of sides, the regions A through E have prices. So we are calculating the prices by multiplying these. So 4 into 4, 16, 16, 32, 4, 12. And if you do a total sum of it, the total cost now comes to be 80 for this. And I'm just curious to see, is it cost effective? Yeah, it seems like it used to be 140. So elves definitely are saving some money in the bulk discount. And similarly, in the second example above, full of XNO's plant, they would have a total price of 436. And in the E-shaped region, that has an area of 12 and 4. And I think they have just explained that. It's fine. I'm going to skip over that in interest of time because we have built the base logic in the part 1 to see. And similarly, there is another example of the bigger one. And then that also has a region inside a region. But that doesn't really matter for us because we will be able to calculate the size. So here also, actually, this is interesting. So if you're calculating the number of sides, it will just follow like how we did for C, where we will create a polygon out of it and just count the number of sides. So I think now is a good time for you to pause and think and maybe take this example here and try to do a dry run on that and think about how you can solve this problem. And what I'll do is I'll wait for you to think. And once you are back, we will discuss some strategies on how we can build on top of the part 1 that we did. So yeah, I'm not kidding. Pause now and think about the problem. So yeah, I hope you paused the video and gave it a thought. And I hope you were able to derive like what we need to do and what we need to change from part 1. In my head, it's fairly straightforward actually for a change. Maybe there will be some retribution, but remember when we were talking up to calculate the perimeter here, that we will maintain a direction vector and then we will maintain a count of every time we move to the next element. Well, in this one, it's exactly the same, but now instead of maintaining the count of each, like counting the perimeter for each direction vector, all we need to maintain is the count of the number of times the direction vector changes. So like, let's say if you're starting from this E and you are moving here because you cannot go up, can't go up, cannot go up. And then when you come here, you cannot go right. So as soon as you change it, you take 1, you come down. As soon as you change it again, you count 2. You come here, you're on an edge, you cannot go down, you cannot go back, you cannot go up. So you will keep going because it's E. As soon as you hit here, you cannot go left, you cannot go down, you go up, you change it. And then as soon as you reach the point back and you turn left, and then you see that you have already visited this direction vector before, you add 1 and then you escape, and that's your number of sides. And we can do this similar dry run on an irregular shape here. So here also, when you start from here, you are starting at 1. You change your direction, you count 2, change direction 3, change direction 4, change direction 5, 6, 7, and back to it, and 8. And eventually what I'm describing you is walking on the boundary of a polygon and then just counting whenever you do a direction change. And I think this should give us our answer pretty much with very minimal change in our code. So with that, I'm going to go back and write some code. And I think you should do the same as well. And once I'm back, we will do some retro based on our discussion here to see what we could have done better.
One eternity later.
And hey, welcome back. As you can see, we have received another gold star. And with that, we have solved and completed day 12. I'll be honest, it took me around 40 minutes to write the algorithm to do this. And there were so many edge cases of this walking the path and maintaining the direction that while doing that, I stumbled upon an interesting idea that instead of we getting this to count the sides, if you look at any polygon, so it's a triangle, square, pentagon, maybe this shape. If you look at the number of sides, it is 3, 4. Actually, I made a hexagon. So 6, 1, 2, 3, 4, 5, 6, 7, 8. If you look at number of sides, it's actually equal to number of corners. And this was a revelation which took care of a lot of edge cases when we were traversing and looking at the neighbor and doing that. Because if you see here, I think we have total number of 3 corners, and here we have total number of 4 corners. Here we have total number of 6 corners, and this will probably not be valid here because we are only going in 4 directions, so you can ignore that. And in this one, this is again, like if you count the corners, it's number of 8 corners. And now writing an algorithm to count the corners, that is much more simpler than walking the edge and then trying to maintain the direction vector. Because in any scenario, so like let's say if we are planting a plant X, there are only 4 scenarios of a corner that can happen. Actually, this also cannot happen here because we don't have diagonals. So all the angles are 90 degrees. So probably this and this are good examples, but hence it still proves this point here, right? And that's a very interesting thing to note. And believe me or not, somehow creating this new camera mask frame every day in Photoshop, that helped me because when I was recording my video, I was just looking at my recorded video and I looked at that and then just it hit me. Anyways, brilliant shit, right? So in our algo, if you look at this, we only have 4 types of corner, where if you have X here, you will have 0, 0 here, you have X here, you have 0, 0 here, you have X here, you have 0, 0 here, and you have X here, you have 0, 0 here. And everything else here is not going to work. And once I was able to figure this part out and look for these cases, I was able to write code pretty quickly, which just found whenever we were looking at our flood fill algo in part 1, or technical terms like a BFS or a DFS, to find the region, I just counted the number of corners. So whenever evaluating an element, I would just look at if it matches with one of these cases, and I would just say corner plus is equal to 1. And that helped me solve this problem. And as you can see, I'm very sleepy right now because it's 1:30. And but yeah, I get a lot of joy out of solving these problems and learning something new. Because let's face it, in your day-to-day production apps, unless you're working on something cutting edge, it's usually just CRUD apps calling a database, using a cache and doing some other things. But we will talk about them more. I have a lot of videos in pipelines and I have been writing scripts for them. But currently all my bandwidth, free bandwidth, and actually more than my free bandwidth, is going to this challenge. And I think it's continue to be like that till 25th December. But yeah, with this, we are at the end of day 12. I hope you had fun solving this problem. And if you're still stuck, I will be pushing my code in the GitHub repository and attach a link below as always. And I will try to incorporate all the test cases so that it's easy for you to walk through them using a debugger of your choice. And yeah, if you like these videos, please like, subscribe, and share with your friends who would be interested in solving these puzzles. And do share some feedback in how I can make these explanations a lot more better. And with that, I will take your leave and you have a very nice day. Bye-bye.